Hello and Assalamualaikum doctor and everyone. We are from group 3. Today we are going to present about experiment 3, which is vapor compression refrigeration. This is our group members, me Alatea Handalita, Andi Suryana, Nur Hazika, and Nurul Hairia. Today we will discuss 7 content: abstract, introduction, theory, methodology, results, discussion, and conclusion. Next is abstract. Refrigeration is the process of transferring heat from a low temperature reservoir to a high temperature reservoir to ensure that the cold region is constantly accessible in the system. The purpose of the laboratory experiment is to look into the vapor compression cycle by referring to the Hilton R71 refrigeration system. Condenser, compressor, expansion valve, and evaporator are the 4 essential components of a refrigerator cycle system. To complete the cycle, it must divert some heat from a low temperature medium to a high temperature reservoir. This mechanism works in a similar way to an air conditioner, in that heat is collected inside the room and cool air is expelled. Lowering the room temperature, the procedure that occurs in a refrigerator, is the subject of this experiment. The purpose of a refrigerator is to remove heat from the refrigerator space, KL, in evaporator. To achieve this goal, the COP was calculated using the value of KH and KL. The heat transfer to surrounding medium is denoted by KH in condenser. The cup of refrigerator can be determined using this equation. COP is equal to desired output divided by required input. However, some inaccuracies that happened during this experiment and impacted the accuracy of the result are detailed in the discussion section. To address this issue, the cautionary additionally suggests in the discussion section that more precise data can be obtained. For introduction, vapor compression refrigeration systems are the most commonly used among our refrigeration systems and is the most widely used method for air conditioning of buildings. Refrigeration is often a vapor compression refrigeration system. When the refrigerant evaporates at low temperature, the mechanical energy necessary to run the compressor serves as the system input. The working principle of a refrigeration system is based on the cycling law of the thermodynamic that is subjected to different temperature sources. Throughout the system functioning, the refrigerant goes through a series of state changes before returning to its original state. A refrigerator operation is based on the removal of heat from a low temperature zone. Due to the law of conservation of energy, the heat is transferred from the substance placed in the unit, plus the energy necessary to run the group cannot be eliminated. The heat is released to the surrounding at a higher temperature. As a result, the machine functions as a heat pump. The heat pump and the refrigeration cycle are comparable. Heat emitted by a heat pump, on the other hand, is used, whereas heat absorbed in the refrigeration process is not in general in the system, can be comparable to a reverse cycle heat engine, technically known as Carnot modified sequence. The heat is transferred from a cold to a hot reservoir, hence in the second law of thermodynamics. The pressure in the condenser and evaporator are measured using pressure gauge. Similarly, heat transfer are installed at the input and exit of the evaporator compressor.
Theory of this experiment. The second law of thermodynamics states that processes take place in a specific direction and energy has a quantity and quality. Heat is a type of energy that is transmitted between two systems due to a temperature differential. The reverse process cannot happen on its own. Therefore, heat that transfers from low temperature medium to high temperature medium requires the use of refrigerators. This is the basic components and schematic diagram of a refrigeration system. Refrigerator is a device that same as heat engines or cyclic devices where the working fluid used is called as refrigerant. The refrigerant is introduced as a vapor into the compressor and compress the condenser pressure. As it passes through the coils of the condenser, it cools and condenses. The low temperature refrigerant next passes through the evaporator where it absorbs heat and evaporates. Therefore, the cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. A refrigerator's principal purpose is to remove heat from refrigerated space which necessitates a work input. The efficiency of a refrigerator is measured in coefficient of performance COP, which is abbreviated as COPR. The formula used is COPR equal to desired output over required input equal to QL over W net in, where the QL is magnitude of the heat removed from the refrigerated space at temperature TL, W net in is the net work input to the refrigerator, and the QL is the positive quantities. Next is methodology. The apparatus used in this experiment is Refrigeration Cycle Demonstration Unit RC33PA Hilton. Next is the procedure of the experiment. Step 1. The components of fluid R141V is identified where the components are condenser, expansion valves, wattmeter, evaporator, compressors, water flow in and water flow out. The thermometer for each position in the refrigeration cycle demonstration unit R633PA Hilton is observed. Step 2. The experiment was started by opening the valve. The water pipe is opened followed by setting up the water flow rate to the evaporator 35 grams per second and set to the maximum for water flow rate to condenser. Step 3. The main switch is switched on. Step 4. The cooling system is allowed to be stable for approximately 10 minutes. The parameters are recorded in the table. Step 5. The experiment is repeated by changing the flow of water to condenser in between 35 grams per second to 40 grams per second. The ready taker is repeated for 4 times. Step 6. After the experiment is done, the device is closed where the flow rate is set to 0 grams per second. The main switch is switched off. The last step, the water supply pipes are turned off followed by closing the valves to the shutdown position after 1 minute.
Okay, so for the result, we want to calculate the rate of heat transfer at evaporator, at condenser, and also for the COP, coefficients of performance. Okay, we have been provided with information such as temperature T1 until T7, and then absolute condenser, absolute evaporator, pressure, and also the power input. So, basically we obtain increasing values for rate of heat transfer, and also for COP we obtain less than 1 values. Okay, the discussion. Okay, this is the calculation for rate of heat transfer at evaporator. Okay, we did interpolation for T1 and T2 by using step table F4. Okay, and then we using formula Q equals to M delta H T2 minus T1. Okay, and then we convert the absolute pressure units, gram per second to kilogram per second. So we get the answer for each test for rate of heat transfer at evaporator. Q1 we obtain 46.23 watt, Q2 we obtain 46.20 watt, Q3 we obtain 46.18 watt, Q4 we obtain 46.13 watt, and then the last one Q5 for test 5 46.09 watt. This is the calculation for rate of heat transfer at condenser. Okay, the formula is same with the previous one. Q equals to M delta H T4 minus T3. Okay, we also did interpolation for T4 and T3 also using steam table F4. Okay, but in this calculation, the absolute condenser is not constant like at evaporator. So we also convert unit kilogram per second to kilogram per second. So we obtain the values for Q1 until Q5. Q1 equals to negative 43.66 watt, Q2 negative 38.66 watt, Q3 negative 28.55 watt, Q4 negative 19.24 watt, Q5 negative 9.60 watt. The last one, the calculation for COP, coefficients of performance. So this is the formula. Q evaporator divided by Q condenser minus Q evaporator. So value of Q evaporator and Q condenser we can get from the previous calculation. Okay, the rate of heat transfer at condenser and at evaporator. So we obtain the value for test 1, test 2, test 3, test 4, test 5. 0.51, 0.54, 0.61, 0.71, and last one for test 5, 0.83.
Next, I will continue for the discussion part. So, two graphs were drawn based on the result. First graph is the graph of temperature T1 until T6 versus compressor flow rate. Based on the graph, the temperature decreased if the condenser flow rate increased. Thus, it shows that flow rate is directly proportional with the temperature. But we can see that the value of T3 and T5 are affected by the changing of the flow rate. So their values are declining as the condenser flow rates increase due to the transferring of heat at the condenser. For the second graph is compressor power versus compressor flow rate. As we could see, most of the tests will increase in the flow rate if the compressor power increase, except for the fourth to the final test setting. As the fluid is being compressed in the compressor, the mass flow rate will increase due to the velocity and therefore will demonstrate the increasing of power. Next is the errors and precautions for this experiment. Students need to make sure the joints are tightly attached in order to avoid any leaking. Next, if there is air bubble inside the pipe, students need to run the water inside the pipe before we start the experiment. Lastly, to avoid the inaccurate value of result, take the average temperature when calculating. That's all from me. Thank you.